Remember that Ørsted in 1819 discovered that a steady current produces a steady magnetic field, and that connected electricity with magnetism. A little later, Faraday therefore suggested that maybe a steady magnetic field produces a steady current. And he did many experiments to show that. It turned out not to be so. And one way he tried that is as followed. He had here a battery with a switch, and here he had a solenoid. He closes the switch, a current will flow, and that creates a magnetic field in the solenoid. And that magnetic field, maybe it runs like so. Depends on the direction of the current. And so now, he put around this solenoid a loop. Let's call this loop number 2. So it was around the solenoid, and let's call this loop number 1, of which the solenoid is part. Whenever there was a current in number 1, he never managed to see a current in number 2. If there is a current going in number 1, there is a magnetic field. And that magnetic field is seen, of course, by the conductor number 2, by that loop. Never any current. And so he concluded that a steady magnetic field, as produced by the solenoid, circuit 1, does not produce a steady current in number 2. But then one day, he noticed that as he closed the switch, he saw a current in number 2. And when he opened the switch, again he saw a current in number 2. And therefore he now concluded that a changing magnetic field is causing a current. Not a steady magnetic field, but a changing magnetic field. And this was a profound discovery which changed our world, and it contributed largely to the technological revolution of the late 19th and early 20th century. A current, therefore an electric field, can be produced by a changing magnetic field. And that phenomenon is called electromagnetic induction. And that phenomenon runs our economy, as you will see in the next few lectures. I have here a conducting wire, a square. I could have chosen any other shape. I try to make you see three-dimensionally. And I approach this conducting wire with a bar magnet. The bar magnet has a magnetic field running like so. As I approach that loop, that conducting wire, moving the bar magnet, that's essential. I can't hold it still, I have to move it. If I come down from above and I move it down, you're going to see a current going through this loop. And that current will go into such a direction that it opposes the change of the magnetic field. The magnetic field is in down direction and it is increasing as I move the bar magnet in. Then this current loop will produce a magnetic field which is in this direction. And when you look from below, the current will go clockwise, producing a magnetic field in this direction. If you move the bar magnet out, then the magnetic field is going down here, then the current will reverse. The current wants to oppose the change in the magnetic field. And that's called Lenz's law. It is the most human law in physics, because there's inertia in all of us. We all fight change at some level. Lenz's law is extremely powerful in always determining in which direction these induced currents will run. It is not a quantitative law. You cannot calculate how strong the current will be. But it's very useful, as you will see today, to know the direction of that current. That gets you out of all kinds of problems with minus signs. I now want to do a demonstration which is very much like what you see here. I have here a loop. That is the square that you see there, except that it's not one loop, but it is many of them. Hundreds, doesn't matter. And what we're going to show you is an ammeter that is connected. So there is somewhere in this circuit an ammeter. I have a bar magnet, and I'm going to approach this conducting loop with a bar magnet. And you're going to see a current running in one direction, and when I pull it out, it will be running in the opposite direction. And when I hold my hand still, so that the magnetic field is not changing, no current. You're going to see the current meter there. And here is my bar magnet. I come close to this conducting loop. Notice, you see a current. I pull back, current is in the other direction. Now I will go faster, so that the change of the magnetic field per unit time is stronger. More current. I go out fast, more current. So you see, it's the change of the magnetic field that matters. If I come in very slowly, which I do now, very slowly, you almost see nothing. And right now, the entire magnetic field is inside this loop. The strongest I can have it. Nothing happens because there is no change in the magnetic field. It's only when I do this that you see the current. So an induced current is clearly the result of a driving force. There must be, just like we had with batteries in the past, there must be an EMF. There must be an electric field that is produced in this conducting loop. And so I create now an induced EMF. We used that word EMF earlier for batteries. So now we have an induced EMF, which is the result of this changing magnetic field. And that, therefore, is the induced current times the resistance of that entire closed conductor, whatever is in there. In this case, the total resistance of all these windings, of all the copper wire. That's Ohm's law. So the induced EMF is always the induced current times the resistance. This loop, the big wire, and I'm going to just put it over this solenoid. Let me first make sure that my ammeter, which is extremely sensitive, I can zero it. It's sign sensitive. If the current goes in one direction, you will see the needle go in one direction. If the current goes in the other direction, you will see the change. And so now I put this loop around here. Crazy shape, this loop. So it's around this solenoid once. So the magnetic field is inside the solenoid. And so think of a surface which is attached to this crazy loop. And now I'm going to turn the current on, and only while the current is changing will there be a changing magnetic flux. Only during that portion will you see a current flow. 3, 2, 1, 0. I will break the current, 3, 2, 1, 0. Went the other direction. If I change the size of the loop, I'm making it now different. Much smaller makes no difference for reasons that I explained to you, because the magnetic flux is not determined in this case by the size of my loop, but is determined by the solenoid. So if I do it again now, with a very different shape of the loop, let me zero this again. 3, 2, 1, 0. 3, 2, 1, 0. No change. Almost the same what you saw before. But the magnetic fields go through all three of them. Therefore, the changing magnetic flux will go 3 times through the surface now. And so Faraday says, fine, then you're going to see 3 times the EMF that you would see if there were only one loop. And if you go 1,000 times around, you get 1,000 times the EMF of one loop. Not so intuitive. So, I'm around now once, I go around twice, and I go around the 3rd time. I have 3 loops around it now. I can zero that, but that's not so important. 3, 2, 1, 0. You saw a much larger current. It's about 3 times larger because the EMF is 3 times larger. I break the current, and you see it 3 times larger. And this is the idea behind transformers. You can get any EMF in that wire that you want to by having many, many loops. You can get it up to thousands of volts.